All right, this is a debrief on the solutions to orbital mechanics skill 1 on doing circular orbits. For this, you need to be able to calculate the circular orbital velocity. That one is v squared equals g times the mass of the central body divided by the orbital radius. Newton's version of Kepler's third law, which says t squared is equal to 4 pi squared orbital radius cubed divided by g divided by the central mass. Newton's law of universal gravitation, which says the force of gravity between any two objects is negative capital G, mass 1, mass 2, divided by the distance from the center of one mass to the center of the second mass squared. And the formula for calculating the acceleration due to gravity, little g is equal to capital G times the mass of the central body divided by, if you're on the surface of that body, its radius squared. All right, so those are the formulas. And when you use these formulas, you have to be careful that you put all the units in kilograms, meters, and seconds. And your velocities will be in units of meters per second. So here we go. Number 1. Planet A has a mass of 4.53 times 10 to the 23rd power kilograms and a radius of 3,900 kilometers. Notice that that's radius, not diameter. Notice that's kilometers, not meters. Calculate the orbital period for a satellite orbiting the planet at an altitude of 250 kilometers above the surface of the planet. So as a little sketch, you might want to indicate that the radius is 3,900 kilometers, but we're above it. So if this little bit here is the altitude, h, that altitude is 250 kilometers. And our orbit radius, r, little r, is going to be the sum of the planet's radius and the altitude above the surface of the planet. So the orbit radius in units of kilometers is a 5, 9, 10, 11, and a 4. So the orbital radius is 4,150 kilometers. Orbital period means we're going to be using Newton's version of Kepler's third law, solving for t. And if you want, you can take the square root of 4 pi squared first. So the orbital period is going to be 2 pi times the square root of r cubed divided by gm. Well, r cubed, just to remind you, if r is 4,150 kilometers, then you're going to actually type in 4,150,000 meters into r. And capital G, the universal gravitational constant, has a value of 6.672, or 3 if you're a nooge, times 10 to the negative 11th power newtons meters squared per kilogram squared. Well, that's why we have calculators, right? So 2 pi square root of 4,150,000 cubed divided by g, which I've stored in my calculator memory, divided by 4.53 times 10 to the 23rd power, enter. And you probably can't see the display, but it says the period is 9,660 seconds, the 3 sig figs. And out of curiosity, if I divide that by 60, that corresponds to 161 minutes. So a little over 2 hours. Now, this planet is not all that different from the Earth. It's between the Earth and the Moon. It's similar to Mars. So a period that's a little over 2 hours for something in a low orbit is reasonable. All right, so there's my answer for number 1. By the way, if I make a mistake, it won't show up on the video, and I'll probably not even notice it till after it's posted on YouTube. Oh well. Number two, so you students have to call it out to me. A satellite is orbiting planet B at an orbital radius of 6,300 kilometers and a speed of 4.5 kilometers, not meters, per second. Calculate the mass of planet B. So I would use the circular orbit formula, v squared equals g times the mass of the planet divided by the orbital radius. And in this situation, we are rearranging the equation to solve for the mass. So the mass is going to be v squared times the orbit radius divided by the universal gravitational constant. Just be aware that you have to express the speed in meters per second. So 4.5 kilometers per second is 4,500 meters per second. And the rest we just plug. Well, I should also point out that if the radius is 6,300 kilometers, then you're going to type in 6,300,000 meters as you plug it into your calculator. All right, so here we go. 4500 squared times 6,300,000 divided by alpha g, enter. And the result is 1.91 times 10 to the 24th power kilograms. So it's in the general class of being an Earth-like planet. Number three, a satellite orbits planet C with a period of days, not seconds, 5.38 days at an altitude, not radius, of 26,000 kilometers above the surface of the planet. Planet C has a diameter, not radius, of 12,000 kilometers. Calculate the mass of planet C. Well, so again, if you do your little sketch, the radius is going to be half the diameter. So the radius is 6,000 kilometers. The altitude is much larger than the radius. The altitude is 26,000 kilometers. So the orbit radius is the sum of 26,000 plus 6,000 is 32,000 kilometers. And of course, in the formula, you'll enter that as 32 million meters. So there's the radius. The period is 5.38 days. And of course, we have to convert that to seconds, knowing that no matter where we are in the universe, we're using Earth timekeeping systems. So when we talk about how many days it is, we don't mean Martian days. We don't mean Mercurian days or Jovian days. We mean Earth days, Earth clocks. So it's going to be 24 hours in one Earth day. It's going to be, 3,600 seconds in each hour. So 5.38 times 24 times 3,600 works out to a time of 464,832 seconds. And yes, I actually write it all out and don't round it off to the end of my calculation for time in meters per second. So we need to solve for the mass. We have the radius, we have the period. So I would use Newton's version of Kepler's third law. T squared equals 4 pi squared r cubed over gm. And this time we're going to rearrange the equation to solve for the mass. That makes the mass equal to 4 pi squared r cubed divided by gt squared. Plugging in all these numbers, 4 pi squared times 32 million cubed divided by G divided by 464,832 squared. Enter. And the result is 8.97 times 10 to the 22nd power kilograms. Number 4. A satellite orbits Earth with a period of 23 hours, 56 minutes, 4 seconds. Calculate the altitude of the satellite above the Earth. So for the Earth radius, it's something you should look up or maybe even memorize by now. I use a value of 6,378.14 kilometers because that's the central body average value of the Earth radius used in the satellite in the software program called SDK. We're to solve for the altitude. So we're going to first calculate the orbit radius and then subtract the Earth's radius from the orbit radius to figure out the altitude above the surface of the Earth. If the period is 23 hours, 56 minutes, 4 seconds, you need to convert that all into seconds. I'm just going to do it on my calculator. 23 hours times 3,600 seconds per hour plus 56 minutes times 60 seconds per minute plus 4 seconds works out to be 86,164 seconds. Great. Well, we don't know the radius or the speed, so we should be using Newton's version of Kepler's third law. T squared, sorry, my camera, I keep pointing in the wrong spot. T squared equals 4 pi squared r cubed over gm. And this time we want to rearrange the equation to solve for the orbit radius. Wow. So on that one, we go r is the cube root of gmt squared divided by 4 pi squared. All right, so I'm going to do this by open parentheses, alpha g. By the way, since it's Earth, you're supposed to, like its radius, be able to look up its mass. I use a value of 5.974 times 10 to the 24th power kilograms. Okay, so G times 5.974 times 10 to the 24th power times 86,164 seconds squared divided by 4 divided by pi squared, close parentheses, raised to the 3 to the inverse 1 power. Okay, so that's how I would put in the cube root of something. I would make it 3 to the raised to the 3 to the inverse 1 power. Enter. And there's my radius in meters. So if I divide this by 1,000, it's 42,163 kilometers. And if I subtract from that the radius of the Earth, 6378, here's my answer, 35,800 kilometers altitude. 35,800 kilometers based on an orbital radius of 42,163 kilometers. Number 5. A satellite orbits planet D with a speed of 4.50 kilometers per second at an orbital radius of 18,000 kilometers. Calculate the mass of planet D. So V squared equals gm over r. rearrange to solve for the mass. In this case, the mass is v squared r divided by g, and we have to work in the correct units. So this is going to be 4,500 meters per second squared times 18 million meters divided by the universal gravitational constant. You have to make sure that you type in the correct number of zeros when you do these huge astronomical numbers. So the result on my calculator is 5.46 times 10 to the 24th power kilograms, making it slightly less massive than the Earth.